We stopped you in the middle of the tutorials. You said that most of you have gotten through tutorials 1 and 2, so by now you should have a list of proteins, a list of peptides, precursors, and their transitions. We will take now a break. We'll do a lecture about how to set up a targeted experiment. And after that point, we will continue with tutorial 3, so a little bit about how to work with assay libraries, and then we'll continue to tutorial 5. So as I said at the beginning of the day, we skipped tutorial 4. It's on your folders if you want to do it. And that will be about retention time and scheduling. So setting up a targeted proteomics experiment. You've seen this slide from Tina, and Tina was basically referring to the fact that in most cases, we have some sort of standard pipeline. When we do in bottom-up proteomics, we do some protein extractions, digestion, some sort of peptide separation, then we do electrospell ionization. And what's different is how we measure. And there are those parameters that are critical to the machine, so we have to provide them. They are obligatory, and there are those parameters which are optional. So far, what you've got is the critical parameters of the Q1 and the Q3. So this is that list of transitions that you can see on the left side of Skyline. And the purpose of the first part of this talk is to discuss a little bit about other parameters that we need to have, like the collision energy. And then in the second part of the talk, we're going to talk about retention times. Since these are extremely important and useful, we'll spend some time discussing those. At the end of the day, it always comes back to this table. So this table has the list of peptides, all the different masses, all this information about the different precursors, and then all sorts of pieces of information related to the acquisition. How much time we want to spend on it, collision energy, and something about retention time. Some of these things are there for visualizations. Those of you who already opened the transition list, so that there's also some information about the protein, the peptide, and the ion. These pieces of information actually are not important for the machine. They are important for us. So let's start with the first one. So as we do targeted proteomics, the first decision that we do is how do we want to acquire the data. So throughout the course, as we mentioned, we move from SRM to data-independent acquisition. So there are those modes of targeted proteomics where you do targeted acquisition, such as SRM or PRM, and then you have to face many choices regarding the precursors, the transitions, depending which type of method you choose. And there are the various flavors of targeted proteomics using data-independent acquisition, in which you spend less time choosing precursors and transitions before the acquisition. You spend perhaps that time after you've done the acquisition. But also there, you also already have to face certain choices, such as what mass range would you like to cover, how would you like to set up your window, etc., etc. Most of the talk we're going to focus on SRM, but sometimes I'm going to make comments about PRM and swath, and these topics will come back to a bit later. But even in the world of SRM or PRM, we are already faced with a lot of other questions, other parameters that we need to think of. Collision energy, chromatography, dwell time and cycle time, retention times. Tina very briefly touched these points. I would like to extend a bit about each one of these points, just to make it clear so that it's always in the back of your mind, how do we refer to these various parameters. And of course, these are all relevant both for targeted acquisition and data-independent acquisition. They will have importance and effects on both of types of acquisition methods. So we'll start with the collision energy. We had a question in the previous session. A collision energy is a parameter that when we do SRM, we have to provide to the machine. And what is a collision energy? Well, it's actually one of those parameters that are set on the machine. The ions arrive into the machines, and we basically want to get the ions to the detector. There are different potentials along this ion path, and the collision energy is just one of them, but the only one that is obligatory to provide when we do the measurements. The other parameters can be set on the machine with default values, and then we don't need to ever touch them. You can ignore them. Different models and different manufacturers will have different architectures. So this is only a schematic architecture, in this case from a Q-trap. But all of them basically want to do the same. They want to get as many as possible ions from the beginning of the path all the way to the detector. The collision energy itself is an offset. It's applied to the Q2. That's basically the amount of it, and this offset relates to the amount of kinetic energy that we're going to give the precursor. And this kinetic energy is going to basically enable the fragmentation within the Q2. Each ion has a different offset voltage, and that can be given to the instrument. And because of that, what we typically do is, what we typically have is from each manufacturer, we get an optimal linear collision energy equation. It looks something in the lines of this. So for precursor ions of the +2 charge state, the collision energy will be the m over z times some sort of factor plus some sort of other factor. And you will see that also afterwards in Skyline. And then we do the same for +3. We can do the same for +4 or +5, whatever we want. What then we do is we calculate for every one of these precursors a collision energy, and this is already implemented in Skyline. So we basically get this automatically in the report for those of you who already opened the transition list. We would then have within this prediction a collision energy formula. There are several provided already by Skyline, and you can add your own. And the formula is implemented along the same format as shown here. There is a concept related to collision energy, and that is collision energy optimization, whereby we basically try to increase the peak intensity by trying different collision energies and seeing which one of them works. So the collision energy formula that we use is somehow optimized for the average peak or for the average peptide according to certain parameters. Usually these are actually done experimentally, and for your project, for your specific needs, sometimes you want to have better sensitivity and you would like to spend some time to try and see if you can improve the sensitivity of your assay, so basically to get more ions. And there's a procedure that's covered in tutorial 4, which we are not going to do, but there is a procedure to do this collision energy optimization. What you get at the end is first you would export from Skyline the same transitions in different collision energies in different steps, and then you would import it, you would do the measurements, you would import it back into Skyline, and then what Skyline will show you is the different peak areas under different collision energies. So this is the regular formula that was used, and then we here, let's say, reduce the collision energy each time by 2 electron volts, or here increased it, and then what you see here is the total area, how it changed according to the collision energy. So in this case, we were actually working pretty close to optimum, so that's good, that's as best. But what could happen is that your machine is actually, for example, tuned around this area, and then basically you're not making the maximum out of your sensitivity. The process needs to be done basically per transition or per peptide, and so it's a very time and sample consuming. Quite often, if we do it, then we do it with synthetic peptides, from which we have a lot. For many peptides, the sensitivity gain is not very large. I give you here a plot from a paper by Paola Picotti that was published in 2010, where she tried to plot what was the gain in intensity for the different transitions that she tried to do collision energy on them. As you can see, for the majority of these transitions, it was 1.5 or less. If you are lucky then, or very motivated, maybe one of your peptides would fall, or one of your transitions would fall in this range, and then you actually benefited from this procedure. Usually, if we do this, then we do this in projects where we are working on a very specific set of proteins. We want to maximize the sensitivity, and so we want to spend a large amount of time beforehand to try and get the maximum out of it. Sometimes we also do it afterwards when we've tried to detected the peptide and we didn't see it, so we say, okay, maybe we should optimize it and then see if we're lucky. The concept of collision energy optimization, of course, can be applied to any other of the potentials, although it is the one most commonly performed, if at all. What is very useful, and this is what I mentioned before, is to different labs have done this in the past to try and do this on a large batch of peptides, synthetic peptides, and try to improve once the collision energy formula for the machine. So I can tell you in our lab we had a student that was working just on improving these collision energies so that all the machines are at their top performance, and from that moment on we just work with the new formulas and forget about those that were provided by the manufacturer. In practice, I would like to stress that collision energies are per transition. So if you remember, each line is a Q1, Q3 pair collision energy. And that means that we could be optimizing one transition and really downgrading another one. So I give you here an example where these are two transitions. Now we're looking at a transition view of the same peptide. You can see that for this transition, we should have worked at the maximum at the default collision energy, but for this transition, if we would have increased the collision energy, we would actually gain in area. Now, Skyline today also allows you to do these procedures and store them, so you can basically do the whole procedure and then save a per precursor or per transition collision energy information, and then always use that for your project. If you do this, I would like to stress another point, is that since we're doing this per transition, then if we're going to perform any collision energy optimization, what we're going to change is the relative intensity. So some transitions might go up, some transitions might go down, and what we get is a change in the dot products. So if you're going to use a library, and the library was acquired with one, on this machine, for example, with one set of collision energy formulas, and then you're going to do collision energy optimization, suddenly your relative intensities, as expressed here by the dot product, here it's 0.7, here it's 0.52, but even without the numbers, just from the distribution of the colors, you can see that there's a difference in the relative intensities. So if you're going to do this, please remember afterwards when you look at the scores, they might have changed. Now this is when we've done the collision energy optimization and the acquisition of the assays on the same machine. So needless to say that this is going to be very important when you do targeted data analysis on every type of workflow, whether we're doing SRM, PRM, or swath. Maybe the library came from one machine, we're doing the measurements on this machine. If we're doing SRM and we have the library from an Orbitrap. So what you should always remember is that the fragmentation patterns of peptides is something that is very dependent on the collision shell and the instrument. And we always try in our lab to work as closely between the two, so get libraries or the assays on the same machine on which we're going to do the final measurements, so that we can have the best match between the two. We have here on a table some sort of a schematic evaluation. If you're going to do your measurements on a triple quadruple, and you're going to then you're going to select your precursors with a quadruple, you're going to fragment with a quadruple CID, that's the Q2, and then you're also going to analyze your quadruple. So of course it's most suitable when you're doing SRM, because that's exactly along the same lines. But if on the other side of it you're going to use a library, for example, that came from ETHZ, and you're going to use this whole setup, then of course you're going to get very different relative intensities, different ions, because ETHZ is of course not suitable for the case of afterwards moving to a triple quadruple. But we already see the differences when we move from Orbitrap data such as Orbitrap XLs into triple quadruples. Please be aware of these different differences and keep them in mind once as you build libraries for SRM, and even more importantly as you're going to be building libraries afterwards for the targeted extractions from data independent acquisitions. There might be quite some differences between these machines if the data came from one machine and then was moved to another machine. Should I explain this quickly? once you've optimized the collision energy, what Brendan is saying is once you've optimized the collision energy, what you can also do is instead of saving a library that was maybe acquired in shotgun, you can also make a library from these peaks, because these peaks are, the chromatograms are actually what we're measuring. We're only using the spectra as a type of reference. At the end of the day, we're measuring peaks. What you can create is a chromatogram library that saves these peaks, in this case, optimized by collision energy, and then these are going to be our reference, and then we are no longer troubled by this difference on what machine did we do this, on what machine did we do that. So you have this option in Skyline as well, but we don't cover it in any of the tutorials, but know that it's available and out there. So just a quick note on other potentials. As I said, along this iron path, there is a lot of different parameters that you can set. If you are going to get very involved in trying to optimize all of these, I can tell you from my experience at least that the clustering potential, which is towards the front of the machine, I've tried a lot to optimize this and not much happens out of it. Usually there's not a lot of sense in doing declustering potentials, at least on a Q-Trap 5500 on which I've worked. And some people, we've heard actually in different courses, that people play with this parameter, that's the collision in cell exit potential. That's what comes after the Q2, before the Q3, and that basically tells you how many ions move from the collision cell into the Q3. And as you can see, most of the time, it's kind of varied, but there are these values where it's really bad. So usually what's provided by the vendor for these types of potentials is quite good. Of course, if you want to get very involved with your method and try to optimize every parameter, these are some of the more commonly optimized parameters. Any questions about the point of collision energy? So the next point I would like to touch on is the acquisition time, or sometimes it's called accumulation time or dwell time. That's this column. We've already heard about it a bit from Tina, and I would like to extend a bit. As you know, you've just heard from Tina, you know from before, the longer the better, meaning what we're basically telling with this parameter is we're telling the detector how much time it should spend, the whole machine setup actually, how much time it should spend on measuring this transition, so this pair of Q1, Q3. And what we want is to have a very long accumulation time, to be very sensitive, but of course, as you've heard, there's sort of a game between acquisition time and cycle time. We would like to have as many transitions as possible, but then it's also a question of how much time do we want to spend on each of these transitions, and that would be related to the sensitivity, so that's the acquisition time. There's also the question of how often do we want to go through this whole list. That's related to the quantitative accuracy, what you've heard before from Tina's cycle time. And all of these things somehow come into interplay. So just to recapitulate, the cycle time is the sum of all acquisition times, and it tells us along the peak when are we going to come back to the same measurement. And although I'm going to talk now about SRM, I would like to remind you that this issue is very important also when you're doing PRM or swath. Just the question is a bit different. So if we're doing PRM, we're not going to ask when do we come back to the same transitions. We're going to ask when do we come back to the same precursor, how many precursors do we want to measure, how much time do we want to spend on each precursor, and then we're going to ask how often do we want to iterate over the list of precursors. And if we're doing swath, which somehow sounds a completely different type of acquisition, but there again, we have windows instead of precursors. So we're going to ask how many windows do we want to measure, what mass range they will cover, how much time do we want to spend on each of these windows, and how often do we want to go back to the beginning of the list. And there are different ways of dealing with that. And you'll hear more about it in the course. I just want to make here the point that whenever you hear about acquisition time, cycle time, it's not just about SRM, it's going to be relevant to any type of chromatography-based type of quantification. So to iterate on this point again, let's say this is a depiction of the transitions that we want to measure. Now we're measuring unscheduled mode, so we basically try to measure each one of these transitions. That's kind of a list of transitions all along the chromatogram, and the thickness of this line tells us what is the dwell time that we're going to spend on it, which corresponds to the thickness of this red line here. So here we don't have a lot of transitions, which means that we don't have a very big cycle time. We can go over this list pretty fast, and so we have many accurate points along the peak, and we cover it pretty well. If we now made the list much longer, so we decided we want to measure more, but we want to keep the same dwell time, then we're going to come back to the beginning of the list. It's going to take us more time, so we will have less of these points over the peak, and then this might affect our quantitative accuracy or how we can reintegrate the peak from the data that we have. One thing that we could do is reduce the acquisition time, the dwell time. So we would make each one of these lines thinner, or each one of these red lines thinner, and then we have more points across the peak, and we have a smaller cycle time. So as you've heard from Tina, it's kind of a balancing act between acquisition time that we want as long as possible, cycle time that we want as short as possible, number of transitions that we want as many as possible, and Tina gave you a few kind of thumb rules. In this game, there's actually at least one more player, and that's the chromatography. So we cannot discuss any one of these questions without first asking, so what's your chromatographic setup? I'm not going to give here an intro about chromatography. I would just like to bring out 2 points to kind of stress the relationship between these different parameters. So when we talk about chromatography, again, very schematically, we have 2 parameters that we discuss. One would be everything related to the gradient. How long is the gradient? What's the slope that we're going to use for the gradient? What's going to be the flow rate? Are we going to use nano, micro, etc., etc.? And then the other parameter that we're going to play around with is what column are we going to use? How long is going to be the column? What's going to be the inner diameter? What kind of particles are we going to pack? Etc., etc. And these different aspects of the chromatography are related to cycle time, acquisition time, and the number of transitions. So if we talk about first, just a little note on the gradients, let's look at a certain gradient, and we have this cycle time. I'm going to ask you, what's going to happen if I'm going to make, here I have a very long and shallow gradient. What will happen if I'm going to make it into a very short gradient and very steep? What do you think will happen to the cycle time? Anyone? So, per se, nothing will happen to the cycle time. The cycle time is a parameter that is set by us. But when we're going to change the gradient, we need to think in advance when we set our method, what's the cycle time that's going to be suitable for our gradient. So if we're going to take a very long gradient and make it very short without adjusting any of the parameters, we're going to reduce the resolution, and here I'm talking about the peak resolution, so chromatographic resolution. We're going to get higher intensities, but since we're compressing peaks, we're going to get less points along a chromatographic peak. So if you're going to make very short gradients, you need to consider that you need to, at least to some extent, reduce the cycle time if you want to keep the same number of points per peak as you had with very long gradients. Is that clear, or is there any question about this part? So let's ask the same question about a column. So we can play with different parameters related to the column, the length, the particles, and so on. Let's take, for example, the particle. What will happen to a peak if we take smaller particles? The peak will be sharper. What will happen to the cycle time or how should we adjust the cycle time? Reduce the cycle time, correct. So this is an example where it's a fairly short column with 3 micrometer peak. Here we have a longer column with smaller particles. And you can see here what's the width of this typical peak and what's the width of this peak. And I can tell you that the person that did the measurements accounted for the difference in cycle time and reduced also the cycle time. But if we would not have reduced the cycle time and we just use smaller particles but don't take that into account, we might miss the peak completely. And it's not because it's not there, it's because we saved the method from someone else that had a different cycle time. He prepared it for a different column, and we just used this, and we use the same parameters, and then we kind of miss peaks just because of this reason. So whenever you think of the the point of cycle time, you also need to think about your LC setup. So we have this interplay between chromatography, acquisition time, cycle time, the number of transitions, and we always want to improve. Yeah, sorry. You can? So in Panorama, what you can do is export your skyline documents, and then you can visualize, you can see other people's. That yes, that would be one of them. As far as I know, the dwell time is not stored in Panorama. Yes. Um, so how can we improve the interplay between these different parameters? What would be at least one way that you've already heard about? So one way would be scheduling. This is what Tina very briefly mentioned, so I will explain it again. In scheduling, we say instead of monitoring a peptide throughout the whole chromatogram, as I've shown you before in this example with the colored lines, we're only going to monitor a peptide that we're interested in only in a specific segment of the chromatogram. So basically we're saying we divide the chromatogram into different segments, and we say monitor peptide 1 only during this segment, and then monitor peptide 3 only through through this segment. The fact is not that we really divide the chromatogram into chunks. What we basically tell the machine is we try to say this is the predicted, or this is some sort of a retention time information, and we take a certain window around this retention time. In order, what this achieves is now, since if we have a very long list of transitions, but if we measure through this segment, we only measure peptides that we expect to elute here, so we go through a shorter list of transitions because we have only a local kind of set of lists of transitions that changes along the chromatogram. And if we reduce the number of transitions, we can increase the acquisition time while keeping the same cycle time. So what we get is, by splitting the whole chromatogram into different segments, we are keeping the same cycle time, but we improve per transition the acquisition time because we can spend more time acquiring it in that local segment. Of course, this is related to the number of attention time windows we're going to use, which is related to how well do we know what is the expected retention time and what is the window that should be around it. So if we only had, for example, here we have 4 windows. If we only had 2 windows, then we would only improve by a factor of 2. But if we had 300 windows and we only monitor each peptide in its own separate window, then of course we can maximize the acquisition time per that transition. So yeah, that's the problem. When we want to do scheduled SRM, we need retention time information. And that, just to iterate for the beginners that maybe don't remember or exactly know what I mean by retention time, I'm going to give you a kind of a formal definition. Retention time in chromatography is the characteristic time that it takes for a particular analyte to pass through the system from the column inlet to the detector under a defined set of conditions. And what happens is that this retention time of a peptide is dependent on a lot of parameters. First of all, it's dependent on the peptide itself, sequence, and all sorts of things that can happen to the peptide itself. Then it's dependent in which sample background we are trying to measure this peptide that we're interested in, what's going to be our chromatographic setup, so that also affects what's going to be the retention time, and different parameters related to the autosampler, although these usually would affect the retention time of all the peptides that we're trying to measure. So the problem with this is, of course, that it's kind of hard to get, or we need to get this from somewhere. So where can we get retention time? One place to start is with your own machine. So, for example, we could do unscheduled SRM, so we could do as we did before, just measure across the whole chromatogram our peaks of interest and try to find the peak, and then we can save in Skyline what's the retention time of this peptide. However, it's not always possible for endogenous peptides where we are not sure where it's eluting or we have no guess. It's very nice to do if you have synthetic peptides because then you can simply inject the peptide and you know what you're looking for. The other option is to go from discovery proteomics. So if you did shotgun experiments or data independent acquisition type of experiments, also there we can extract from these files, we can extract the retention time, and Skyline actually does it when we build libraries within Skyline. It will save the information on the retention time, so that's another source of retention time. We can also go to databases. Sometimes they will contain empirical or predicted retention times, and of course then comes the question, how were these data sets acquired, on which machine, on which LC, and so on, or how well did they predict the retention time, so we always need to be aware of these considerations. And the other option is when we have no idea and no clue what we're looking for, is to use retention time prediction. So there are online tools such as the sequence-specific retention time calculator, SSRCalc, which is implemented in Skyline, but it's also a web tool if you want to use it, where you give sequences and some information, and then it tries to predict a retention time. And I have to say, it does a reasonable job, so it's better than nothing, and in most cases, it will get a guess that is fairly reasonable. So in general, we always say, even if you don't have any information, some information, for example, from SSRCalc is better than the no information, and that's always a good place to start. But it's not the only place, and there are ways to do it better, and this is what we're going to be explaining. How does scheduling work in practice? In practice, it depends a bit on the vendor. So basically, what you do in AB Sykes machines is you indicate the expected retention time, so it's a time now in minutes, and then on the method, you're going to say what window you want to do around this expected retention time. So in this case, it would be plus minus 2 minutes around this, or for example, plus minus 10 minutes around this expected retention time, and then the machine will calculate all the windows and do the measurements, and when you will import the data into Skyline, you will only see this window. If you're using thermo machines, you need to specify the window yourself. So you need to say, I want to start from this time point and to stop at this time point. What is nice here is that you can set different windows for different peptides. So some peptides, if you think you know very well, can have a very narrow window, and for other peptides, you can have a very big window. This depends a bit how much you tamper with the method, but that is possible. And nicely enough, everything is implemented in Skyline, so you don't really need to worry about it. What you do is you set which type of machine you want to do, and then you say that you want a scheduled method. It will go into the files and get retention time depending how you set the retention time parameters, and then you will export the method that is already set up for your machine. A last note on scheduling and retention time before we continue to the next topic, and that is when we look at retention time, till now I was mostly explaining it in the context of scheduling, but that's of course not the only time when we use retention time. And if you remember already from the talk of Tina, we use retention time for scheduling in SRM and PRM, but we use retention time in any type of targeted proteomic workflow, also for the identification. So we had this example when we had 2 peaks and we didn't know which one, but if we had prior RT information, that would help us to choose this peak. And this is relevant for any type of workflow. So it's always good to have retention time, and you can always use this piece of information to improve on the identification, or at least give you an idea. Is there any questions so far on the topic of scheduling? Yes.
I know it from the Trello software. Then you get a visual graph of your scheduled method, and which is calculating the cycle time for every, let's say, over the retention time. Is there any
So we will see this in the tutorial. So the question was, let's say we have different windows, then it's going to implicate the cycle time if, if let's say at the beginning or at the end of the gradient, for example. Did I understand this correctly? So what you have in Skyline, and you will see this afterwards in the tutorial, is you're going to get a plot that tells you with this window how many precursors are you going to measure, and then it's going to be sort of a cumulative plot that tells you in this, and then visually you will see that in this part of the chromatography you're going to be measuring a lot of precursors, and in this part of the chromatography you're going to be measuring a few precursors. And of course what you can then try and do is adjust the chromatography or so to sort of distribute or adjust the window and so on. It will not tell you, as you explain now in Pinpoint, it does not tell you what's going to be the final cycle time, but you can estimate it. In other machines you set the cycle time as a forced in a parameter, and then you basically don't have this option as you described. Any other question? Yes. So the problem of coeluting peptides is indeed a problem. Could you explain what you mean by this question? Mm-hmm. Yes. Mm-hmm. So since you're doing targeted measurement in this case, then so in the case of targeted measurements, you will have different transitions, so different pairs of Q1, Q3. So these are going to be separate peaks, and then the only question is, of course, a question of chromatographic resolution. So if you have a very short gradient and these peptides have the same Q1, Q3 pairs, for example, for some reason, and they will also coelute chromatographically, then Skyline will not solve this problem. It's up to you to improve them. Then you will get two different peaks, and that's not a problem. Other questions? Okay. So we have retention time. We say we need retention time, or we would like to have retention time, and we say that it's dependent on all of these things. And ideally, if we could eliminate this dependence on sample background, chromatography, autosampler, etc., we would it would be easier for us to use retention time. We would have some sort of standard. And the question is there a way to standardize RT information so that we could store it and transfer it? Does anybody know one of these ways? Mm-hmm. Correct. So a person here mentioned peptides from a company called Diagnosis, and we'll look exactly into that. In order to explain this, I need to explain a basic concept, which is retention time index. So let's say we have, and I'm sorry, I'm not very good at doing pictures in PowerPoint, so imagine that this is a peak. We have some sort of analyte, and we measure this analyte, and it elutes at 11 minutes. And the thing is that if we afterwards go to a different machine, maybe it's not going to be 11 minutes. Many years ago, in the 50s actually, there was a Swiss chemist, and he came up with an idea called retention time index. He was working on a different type of chromatography and doing something completely different, but I'm going to use this term nevertheless. The idea about retention time index is that if you would measure this analyte between two standards, so the peak comes between these two, you could somehow make a standard out of the retention time of this analyte. So you could basically calculate when is this analyte, how far is it from, let's say, standard A, how much before is it from standard B, and what you would get is a number. And this number, which we call a retention time index, is used to store the retention time of the analyte in relative to the retention time of the standards. And what you see, if you could all look up, before we had a scale in time, so this was 5 minutes, 11 minutes, 15 minutes, and when we do this process of using a retention time index, we move into some sort of value that actually doesn't have units. It just tells me this is this and this amount after this standard, and this amount before this standard. So this is one way of storing information, because we store where does our analyte elute in relation to standards. Of course, we can use it the other way around. We can use it for the purpose of prediction. So if we want to try and guess where is our analyte going to be, so we're not sure is it going to be in this time point, or maybe it's going to be in this time point or this time point, what we can do is we can measure our standards. Now we're measuring them on some sort of chromatographic setup. We get in minutes where do these two standards elute. Then we need once to get some sort of a retention time index, so we need to get it from somewhere. Let's say we have it. Using this retention time index, we can calculate back what is going to be the retention time in minutes. So if we knew the retention time index of an analyte, we can predict the retention time of the analyte in minutes. Before, we didn't know where it is. Then we measured standards, and then using the retention time of these standards, we could predict where does the analyte elute. And what is nice about this is that it's practically independent of chromatography, meaning whether we use a very long gradient or a short gradient, we can always do this prediction step and predict where is this analyte going to elute. Are there any questions about this very basic concept, retention time index? Yes.
So has Skyline a concept to?
Yes. Otherwise, we wouldn't teach it.
So I just got by explaining.
Yes. I will explain this in a moment. So, here we called it retention time index, and that is the fact that we're going to index retention times of analytes in relationship to standards. And in proteomics, quite often, or the terms that we use the most commonly, but there are certainly other terms, is an IRT value, and that would be maybe, some call it independent retention time or index retention times. We're actually never sure what's the real meaning of I. Maybe it's just iPhone, but the point is that it has a bit of a different name, but it's the same concept. So how would it work in proteomics, the IRT values? What we use as retention time standards is a set of peptides, and these peptides are going to be spiked into our samples. And for these peptides, we know the IRT value. So this is something very important. Someone in advance already figured it out, and he knows what's the relationship between all of these standards. So before we had an example of only 2 standards. If we would have more, we would also like to know what's the relationship between all of these standards. That would be the IRT values, and they are provided. Then, whenever we go to a new machine, or our machine, but we change the column, we can measure the RTs of our standards, and that will give us a value in minutes. So first we had IRT values that were provided, we knew them. We go and measure these values on a machine, and then we get some numbers in times. The next thing that we need to do is we need to get an IRT value for our peptide of interest. And this, unfortunately, needs to be done once. So at least once we need to measure in real time our analyte in compared to the standards. We cannot always just guess it. And then we will know what's going to be the IRT value of this analyte. But if we did it once we've done the measurement in times, we can just predict the RT of our analytes in minutes from the IRT value that we had without any units. So we move from a set of measurements that has no units into a set of measurements that has units in minutes, and that is based on the fact that we have these RT indexes, these IRT values, and some sort of knowledge about what's the relationship between these various standard peptides and our analytes of interest. Of course, if we had only one analyte, it's quite a lot of a hassle. But if we have many or hundreds or thousands of analytes, then it becomes very useful. And the main point where it's useful is because, of course, we can also store these values. So where do we get RT standards? There are different ways to approach this topic. One of them is commercial kits, such as the one mentioned here from Biognosys, from Pierce, from Sigma. they sell sets of peptides. For these peptides, there are already IRT values provided. It is provided with the kit that you buy, and then you can go ahead and start working with them. You need to measure once your peptides in relation to this commercial kit and then start working. There are also other ways of doing this. If you don't want to buy a commercial kit, you can also develop your own standard peptides. For example, if you would have synthetic peptides or endogenous peptides that you can always measure. What is important here to mention, and I just give you a few rules, just always to keep it in mind. Usually it's good to have 10 to 20 peptides, so don't have just one or two, because if one or two changes, it's kind of hard to guess. So you need at least two, but the more the merrier, but also you don't need 50 or 60. You would like to cover the whole range of the chromatogram, so if you decide to develop your own RT kit, then don't have peptides that only elute early or only elute late. Try to cover the whole range of the chromatogram, because as we said, we're going to try and use prediction along this whole chromatogram. And of course, it is very advisable that these are of high quality and abundance in all the samples. That's why we use synthetic peptides that we can simply add to all the samples. We need these peptides afterwards in order to do the retention time prediction. So if sometimes they are detectable and sometimes they are not detectable, then it's not exactly ideal. Are there questions? Yes. Should they, sorry? Be heavy? No. There is no, it is not obligatory that these are heavy peptides. They can also be light peptides, as long as they are not exactly the same as light peptides from your samples. So, because then you would have an interference if you're trying to quantify exactly the same protein.
I would guess that most people working with these retention time standards buy commercial kits, and so a lot of people had already worked and tried to establish or found out the best transitions. Are there any repositories where I can get these transition lists, maybe even the optimized parameter for different instruments?
So for the commercial kits, it's provided already when you buy the kit. For if people use their own standards, then it's up to them to deposit or not deposit this. So this I'm not aware of. Any other questions? So what we use in the lab is a kit provided by Biognosys, and I'm going to use this kit because this is what we use and we're very familiar with to exemplify now in practice this concept. So what is this kit? It's a set of 11 peptides, and when you get the peptides, they cover the whole chromatogram range. They are non-naturally occurring synthetic peptides, so they went through different databases and tried to find sequences that don't match into any protein, so you could spike them in different sample backgrounds without worrying that it matches a light peptide from one of your organisms of interest. And as I said, they cover the whole range of the chromatogram. And when you buy the kit, you also get this set of IRT values. So this they already calculated. I have to say it's on columns packed with C18 materials, so if you use other columns, then this values will not hold. But assuming that all of you do, then you can use these IRT values. And now what we're going to do is look, how do we actually do this? So we have a set of IRT values, and then we said the first step is that we need to know the IRT values of these standard peptides. In this case, it's provided, so we don't need to do anything. We just take the table. Now we're going to measure the retention time of our standards on the LC system. And what's going to happen is on the x-axis we have an IRT value, so that's these values. Now they are transposed on the x-axis. And on the y-axis we have a measured time. And what you see is that there's a linear relationship between these two, and for this linear relationship we can also derive a linear equation. So there is we can convert these IRT values, which are indexed values, they don't have any unit, into retention time in minutes that has a unit of a minute, using a linear dependency. And then we usually use as anchor points something that depicts where 0 is and where is 100. And what it works very nice is that this linear dependency between the RT values and the retention time that is actually measured in minutes is always linear, and it doesn't depend on the gradient, it doesn't depend on the type of machine that you use, whether it's an exigent or a proxion, or a long gradient or a short gradient, so it always works. And this is also, if it always works and it's always transferable, then of course it's a very lucrative type of value that you can use because it's very easy to transfer between people. Now we have a targeted peptide that we're interested in. We said the first time that we want to work with this IRT concept with standardized retention times, we need first to get an IRT value for it. So we measure our targeted peptide of interest, and we measure it in the context of all of these IRT peptides. All of them are measured together, so we know where this peptide eluted in relationship to to all the other standards. In this case, let's say it was 21 minutes, so we can use this linear equation, and then we are going to derive an IRT value of 35.9. And this is the value that we're going to store, because this value, as you just said, is independent of the chromatography, so it's going to always be the IRT value for this peptide. And this makes it something that is storable, transferable, and very convenient for you whenever you want to go back to old files, or whenever you want to provide a collaborator with a method that he can immediately implement. And as you saw before in this big table that Tina showed you, there were normalized peptides, and these are these values, 88, minus 13, 33. So these are the stored values, and they match to this axis. And what we said now is that we are going, once we have them measured and stored, we can use them for prediction. So we're going to take these values, we're going to map them on the IRT axis. We know now this minus 13, 33, 88, and now we're going to use the same linear equation and derive retention times in minutes. So now, based on these IRT values that I stored and were independent on of the chromatography, I measured once my retention time of these IRT peptides, of these retention time standards, and then for all the other transitions that I had, I just predicted the retention time based on their IRT values. So I needed to measure 11 peptides to make the linear equation, but then I can predict for hundreds or thousands of peptides their retention time based on this linear relationship. So we move from an IRT value that is provided in a table, stored and transferred, into a retention time, a predicted retention time in minutes. Is this clear, this movement between these values, or should I? Any questions? Anybody has a suggestion why?
Exactly. It all depends on how these IRT values of the standards are defined. And when you see, so what the diagnosis team did is they defined actually the second eliciting peptide as 0. Not the first eliciting, but only the second. This is why this whole scale can also get negative at 1 point. It doesn't mean something is wrong, it doesn't mean it didn't work. It's just the scale that we defined at the beginning. IRT values, yes, can be negative. Not in this case.
Yes?
That means if you want to compare, it's doing the same kind of similar study, if you want to compare your result with the result from other data, you have to use the same set of the standard. Yes.
So if you want to compare two data sets and they came from different labs and they also use different chromatographies, you cannot look just at the table and say, well, if this peptide eluted at 50 minutes and for the other lab it eluted at 30 minutes, it's not, you wouldn't know if this is the same peptide, just different chromatographies, or this is the wrong peak identified on two setups. But if for two labs they would both convert to IRT values, this is a value that you could compare. If what
IRT, they have to, both labs have to use the same kind of the standard to
So in theory, yes. In theory, it would be, or let's say in an ideal situation, both of them use the same IRT kit and then the values are transferable. Although you could envision a situation where that doesn't happen and then you need to convert one into the other. So you could create two IRTs, a linear relationship between two types of standards, and then do two transitions. But it's a bit more complicated. But there are also situations where people did not measure with a retention time, with any retention time kit or any retention time standard, and after acquisition they try to standardize this using other peptides or something like this. That's also a possibility.
Can I add just very quickly? So it's definitely true that it's possible to compare IRT values IRT just not immediately. You must do one more conversion step to take language. But it's not that they are lost. This is always possible because there will always be shared templates between both labs. And these ones you can use them to make a good calibration. It just takes one more important step.
Any more questions on this? So just to reiterate, here we had a case where we had IRT values and we converted them back into retention times, and these are basically predicted retention time. We can go and measure them. We can go and see if this is exactly the same or how well was the prediction, etc., etc. In Skyline, as was asked, all this concept is implemented, but there are two steps that we need to implement. One is the way that we go in this direction, so how we calculate IRTs, that would be a calculator. And then in the second direction, when we have a calculator, how do we predict retention times? And you'll see this in the tutorial. But what we know is that empirically these predictions are pretty good. So this is a figure from this paper when they took a set of peptides and then they once did a prediction with SSR calc, once did a prediction with IRT, and then as you can see, this will have a big impact on the window that we need to do, for example, for scheduling, but any type of application where we want to use retention time prediction for scheduling or identification or etc. So here we have a very small, here we have a pretty big spread of 10 minutes. Here we have a pretty small spread of 2 minutes. And this is, of course, going to be useful in every type of step that we do, any type of analysis we're doing, SRM, PRM, or swath, or any type of data-independent acquisition. So since this is based only on the peptide sequence and this is based on empirical data, this is more accurate, and therefore we also always recommend to use these empirical types of retention time prediction. However, as I mentioned before, if you had no information, then this type of prediction is still better than nothing. So SSR calc should be the minimum that you use, but if you can use empirical retention time prediction, then that's going to be much more accurate. So just to mention here that both of these pipelines are supported by Skyline. So if you want to use SSR calc, then it's already implemented in Skyline. And if you want to use retention time prediction based on the IRT concept, this is also implemented. You'll do a tutorial about it. But basically the way it works is you set a calculator and a predictor, and then you set up the standard peptides, those that are provided from the kit, or those that you made yourself, or those that you got from a collaborator. You need to paste in the sequences, and then you need to paste in these RT values that you got from the provider, and then you can start you can start calculating RT values for your measured peptides. You can use these afterwards for predicting in new methods, etc., etc. Everything is implemented in Skyline, and you're going to do a tutorial about it. So in this talk, we tried to cover a little bit about the different choices that you can do in targeted proteomics. The first one is, of course, how you want to acquire the data, whether you want to do targeted acquisition or data-independent acquisition. And this already entails different choices, the precursors or the transitions that you want that you want to measure, or the setup that you want to use for data-independent acquisition. We'll hear a lot more about these choices down the road in this course. And this, as I said, entails many other parameters that we need to think about when we want to set up our experiment. We first discussed collision energy as one of those parameters which are obligatory to provide with when we do at least SRM. They're also obligatory to provide in any other type of measurement that you do, but sometimes it's just one value that you set, or you set some sort of ramp. In the case of SRM, you provide you provide it per transition. We talked about collision energy as a mean, optimization as a mean to improve sensitivity, and then we talked about how collision energy will affect relative intensities, and this is very important for points down the road. We very briefly touched on the topic of chromatography, dwell time, and cycle time to discuss a little bit about the relationship between these two. We didn't get too much about the basics of chromatography, but we just wanted to bring out the point that you should remember that there's a relationship between cycle time and chromatography, and this will affect, of course, the acquisition time and the number of transitions you can do, all, of course, also in the context of scheduling. And last, we discussed quite extensively the concept of retention times, since this is a concept that we use throughout the course, and explain a bit about this whole concept of using retention time indexes, how to convert retention times in minutes into IRT values that don't have a unit, so that we can store them, transfer them, use them again and again for retention time prediction by using a set of standards and then measuring our peptides in relation to these standards. With that, I would like to thank a few people that also contributed to this presentation, and also Systems X that funds our course, and I'm happy to take any questions if you have. Questions? So the recommendation to work with Y-ions came, as you mentioned, from the fact that when we want to transfer libraries between machines, quite often happens that the Y-ions are more conserved and we can use them more easily. B-ions, depending on the type of fragmentation, sometimes degrade very fast, and then we are only left with small B-ions and we don't see the whole series. It depends a bit on the setup of the machine. Usually we start to work only with the Y-ions, but sometimes B-ions are very informative and we still try to use them, and sometimes they're also very intense. Particularly, or unfortunately, depending how you look at it, smaller B-ions can sometimes be very intense, such as B3 or B4, because the B-ions continues to fragment. More questions? In our lab, we always work with IRTs, not only in targeted, in all the measurements that we do in the lab. And the idea behind it is retention time, figure of speech, but not really, comes for free. It's always there. The kit doesn't come for free, but the retention time does. And if we have it in all the samples in the lab, we can always use it as a standard and always come back to these IRT values. So by having it in every shotgun run, in every SRM run, in every swath run, we can always converge back to these IRT values, and this allows us to have different people working with different columns, different machines, different setups, chromatographic setups, but always with the same value. So it creates kind of a common language. I do know of places that don't use it very often because they have exactly the same LC setup on all their workflows, and then retention time is actually hopefully is fairly stable. But in cases where it's not, or if you want to store it and transfer it afterwards to someone else, then you would need some sort of standard to make the connection. Yes? So, to some extent, yes. However, please consider, so the question was, can we also use these IRT peptides for normalization? To some extent, I would say yes, because we have here an external measure which should have been spiked in all the samples. On the other hand, it's only a very few points to normalize by, and some of these peptides might be subject to some modification, or maybe they lose a bit, so you're normalizing on very few values, and I would warrant against this. But they do abide to the concept that it's an external standard that is spiked into all the samples. But there are, I would suggest, other ways to do normalization between samples that would account more about the variability of the sample itself. This only accounts for the variability of the spray, and etc., etc. Other questions? Good. Of course, if you have also questions later, we can also discuss this later. How we do now is we continue with the tutorials. How many people finished all the way till tutorial 2? I would say almost everyone. So should we now discuss tutorial 1 and 2 and then